So here we go. Rush sigma pi. So I made up a GSA about sigma and pi bonding diagrams, which I'll do today in lecture. And I went with the theme of like fraternity, sorority, so sigma pi. After our intro, we'll continue with chapter 1 today. Maybe we should finish chapter 1 today, I think. Yeah. So that'll affect the due dates of the homework. And as always, come to Caitlin's sessions, except for not today, because it's that one's supposed to meet in person. And yeah, we're not on campus right now. And then to honors tryouts, those were due today and they're due today and tomorrow. But you could turn in those tomorrow if you're supposed to be in the Wednesday lab today and you're done the honors tryout. Just give it to me tomorrow if you're on campus, or you could submit it on Canvas, or you could just give it to me on Monday. That's fine too. So there's the honors stuff, honors tryout. I was reading the chat there. Okay, and then assignment due dates. So, okay, assignment due dates. So I got a lot of things coming up. We should be having the curved arrow quiz today and tomorrow, but we can't have it today. So we'll just have that on Monday. But then I'm assuming we'll meet tomorrow, Thursday, for lab. So we'll have the quiz just as usual for that Thursday lab. And then spectroscopy intro, how to use your NMR, how to use your IR, keep working on those. Extra credit, past peer, let me know. Go to 3 of them, get 3 extra credit points. And then office hour, if you haven't already done it, a lot of you have, but you can still come in. And I think I have the due date September 8th, but if we could have done it today, but if you can do it, try to come tomorrow if you can. If not, maybe Monday, I'm fine with it. And then honors tryout, that's due then. It's actually, that pushes that back if you need it. Solubility of organic compounds. That's the first like wet lab chemistry we'll start doing. We've been working on the NMR and the IR so far, but start preparing for that. And I broke it up. And as I was breaking it up, I was like trying not to make it so you have too much to do at once, but I also want to get through that. I'm in this limbo of like my old online material. A lot of it, I'm like, oh, it's so good. I should have them do it at home before they come to lab, but then I don't want too much to be done. So I'm kind of working on that, but start checking that out so you can start that experiment. And then homework A, I have a due date now. It's the first half of chapter 1. We've covered enough of it now that you should be able to do it all. And so do that, turn it in on the 12th and the 13th. When is that? Is that Monday? I think that's Monday. Yeah, Monday, Tuesday next week. So turn that in, the homework A, and then spectroscopy intro, keep working on that next week. Homework B, we're going to have that due also next week on Wednesday, Thursday. So 2 homework assignments due next week. And we're going to have this quiz about acid-base chemistry. Okay, breaking up the lab assignments. That's this guy. I'm still figuring out this part with the solubility of organic compounds, a new one, because some of it's kind of long, but I'm like thinking maybe they don't need to watch that long video. I could just show them in lab or something, but it's there for us. And then yeah, just try to get through the reading parts of these before each lab period, so that when you come in, you don't have to read the intro, you're just doing the lab work. And I gotta hide this guy. Hide. There we go. Okay, and then feel free to get ahead on this. It's good. And here's a little bit of a snippet of the schedule. So today was meant to be curved arrows quiz, but we'll still have it tomorrow, Thursday. But that'll for Monday, Wednesday lab people, it'll be Monday. And on the Tuesday, Thursday labs, we're completely trained through on the NMR and IR. Everyone's been trained. On Monday, Wednesday, we still need to do some training on that. So we'll catch up on that on Monday. Still prepare for solubility, so we're not falling behind. And if you want, anybody from Monday, Wednesday, if you would like, you can come by lab tomorrow if it works for your time, and you could see if we could get you trained on the IR NMR. Get that going for you. Yeah. Oh, and exam 1's coming up week 5. So we have today's lecture, 1, 2, 3, 4 more lectures before exam 1, and I'll give you more details about exam 1 on most likely this next Wednesday, a week from today. I'll give you more details. All right, and then snap order of operations. So most everybody's been on the NMR now and been trained, and I just want to quickly go through this slideshow to help get these commands stuck in our head so we can get on the NMR and use it quickly. So the software used to be called Nuts because it could drive you nuts, but now it's called Snap. So here's Snap Help for OChem Nuts. So after you've gotten your proton NMR you've done first and you've shimmed it and set TMS to 0, then you bring that free induction decay FID from the PNMR software into the Snap software with the command A2, and then you double click anywhere to get into which command, which subroutine does that bring you into? Can anybody remember?
Base.
Yeah, and if you want, you can you type it in the chat too. Let's see if I can get my chat up. There it is. So when you double click, I heard base. Maybe you type in the chat. What do we get when we double click in Nuts? I mean in Snap. Yes, Zoom. That gets you into the Zoom subroutine. And then you can drag a box over your area you want to zoom in on. And then after you're done with the zoom, then you hit what to get back to the base level? Enter. Yep. You hit enter and that brings you back to base level. And then the next thing we do is we type NOAA. And what does NOAA do? It gets us into the note subroutine and gives us a text box to add a note. So we'll type our name, the sample, and the conditions of it, like is it diluted in a solvent or not. And then we'll also we'll move that note wherever we want. And then what do we do to get back to base level? Enter. Good. And now we're back to base level. The last thing we do is ID. What's ID do?
For integrate.
Yep, it's for integration. And then we double click on one side of a signal, single click on the other, double click on a single click, double click, single click. And then we click one of them once and type V to get the set of value, like, oh, that's a 2-hydrogen signal. And then the other ones are referenced off of that. And then after we integrate, do we hit enter to get back to base level? No, we just hit P to print. And that'll print it for us. And then we got our proton NMR. And now for carbon NMR, it's easier. We start base level. We bring over the FID with control F3. It's different than A2 for proton. And when we do that, it asks us about line broadening. So we accept the 0.5 value by hitting enter. And then we use the mouse wheel to adjust the peak heights, so we don't have too big of a baseline. Then we hold the mouse and type M to get the peaks labeled below or above that horizontal line. And then we double click, and what's double click bring us into?
Zoom again?
Yep. Get back into Zoom, and then we zoom around our areas we want. And then how do we get out of Zoom? That's right, enter. We use enter in this Snap software to get back to base level. And then NOAA for what? For notes again, right? And then finally enter to get out of notes. And we don't integrate, so we just type PL. And what does PL do? Prints. Good. And then we're done. Good job. Okay, done with that one. All right, so I want to do a quick review of hybridization practice, what we went over last time, because we'll need to be really good with hybridization to do sigma pi bonding diagrams I talked about. So first off, the central atom, if it has two atoms or lone pairs of electrons, if it has two atoms or lone pairs of electrons, so you got two atoms or an atom and a lone pair kind of thing, what will be your geometry around that central atom?
Linear.
Yeah, those two things want to be as far apart as possible, so linear. And if you're linear, then what hybridization do we say you have?
SP.
Yeah, it means you're SP hybridized because you have just two hybrid orbitals you need. And these two hybrid orbitals are made from a single S and a single P to make two. And then how many P atomic orbitals are left over that are unhybridized?
Two.
Yep. That's good. And so, yeah, you look something like this. If I represent the SP hybridized orbitals, it's just lines. Those are my two SP hybrid orbitals. I have a P orbital unhybridized in the plane of the page, and then a P orbital unhybridized coming in and out of the plane of the page. So I got two extra P orbitals. All right, so now what about when we have an atom with three atoms or lone pairs or lone pairs attached to it? What kind of geometry would that have? You could type it into the chat too if you don't want to unmute.
Trigonal planar.
That's right. Trigonal planar. They want to be as far apart as possible. Trigonal planar, 120 degrees apart from each other. And what hybridization do they have then?
SP2.
Because you need three sp2s to be trigonal planar. And then how many p orbitals are left over? If we used up a single s and two p orbitals. Yep, one left over, one p orbital left over. And it'll look like so. There we go. We've got three sp2 orbitals, trigonal planar, and I drew these ones coming in and out of the plane. And then when they're drawn this way, the sp hybridized, the p orbitals in the plane of the screen there. It's perpendicular to the trigonal plane. And now finally, when you have four things around you, what's your geometry? Tetrahedral. And so what's your, because tetrahedron has four things as far apart as possible, all at about 109.5 degrees from each other. And sp3, that's right. sp3 is your hybridization. And how many p orbitals are left over if you've used up the s and all three p's? Zero p orbitals left over. Good. And so you look like this. No p orbitals left over. You can't do any pi bonding. You need p orbitals to pi bond. So that's another good question. How many pi bonds can an sp3 hybridized carbon make? Can make 0 pi bonds. What about an sp2 hybridized carbon? How many pi bonds can it make? It's got one p atomic orbital, so it can make 1 pi bond. And if you're sp hybridized, how many pi bonds can you make? You make 2. Good. I got some Venn diagram jokes on here. All right, quick finish up here. This boron right here, how many hydrogens are attached to it? Zero hydrogens. And so how many atoms and lone pairs are surrounding the boron? It has 0 hydrogens. Good, 3. And so if it has 3 things around it, what's the electron geometry? Trigonal planar. And so what's the boron's hybridizations? And hybridization is sp2. Got it. All right, what about this nitrogen over here? How many atoms and lone pairs surround that nitrogen atom? Four. Oh, I'm sorry. I skipped the hydrogen question because my Zoom menu is blocking it. It has one hydrogen that's drawn out. And so it has 4 atoms around it. So electron geometry then is tetrahedral, and its hybridization, sp3. Yep. How about this one over here? How many hydrogens on that carbon? Good, 3.
3.
And then, yes? I'm not sure if someone had a question or they just were unmuted. Okay, I'll keep going. So yeah, secret hydrogens. So that carbon has 3 secret hydrogens, and that gives it 4 atoms around it. 3 hydrogens and the 1 carbon. So what's its electron geometry? Tetrahedral, and its hybridization, sp3. Good. And then this guy, how many hydrogens does that have? 0 hydrogens. Good. And so atoms and lone pairs surrounding that atom, that carbon there. 3. So if it's 3 things around it, it is what? Trigonal planar. Because the 3 things want to be as far apart as possible. And what's its hybridization? sp2. This one, number of hydrogens around it. 0 hydrogens. Atoms and lone pairs. Just 2. So this carbon just has 1 carbon there, 1 carbon there. And then the geometry. You have 2 things, they want to be as far apart as possible. Good, linear. And so what hybridization does it have if it's linear like that? sp, good. And then here, how many hydrogens? 1, good. Atoms and lone pairs? 3. And then electron geometry. You have 3 things, you want to be trigonal planar, good. And your hybridization then is sp2. This one, how many hydrogens does the oxygen have on it right now? 0. Atoms and lone pairs around this oxygen? 4. And then electron geometry. 4 things want to be as far apart as possible, tetrahedral, sp3. And now the fluorine, it's an outer atom, not a central atom. It's got 0 hydrogens on it. And then atoms and lone pairs, 4 total, 1 boron and 3 lone pairs. So electron geometry, let's just go with not hybridized. We'll just not consider the geometry since it's the outer atom. We're good with that one. So we'll call outer atoms not hybridized. Okay. It's a good warm up. Now back to our outcomes. Any questions so far?
Not that it really matters, but would it be wrong to say SP squared or SP cubed?
I've never heard it, but if you said it, I would understand. But probably, I think it's probably not good to say it because then it's you might think it's more than like. I was actually considering just the other day. That's interesting that you say that. Like, why do we tend to superscript the 3 and the 2? Like, I was like, why don't we subscript it? You think we should
Yeah.
subscript it like it's atoms? We subscript, right? I don't know why
Yeah,
that is done that way.
that's what I was wondering, yeah.
Yeah, good
I like
question.
it's a time saver.
To have it superscripted instead of, yeah, I'm not sure.
Probably one of those
Uh,
things where the first person who did it, people just stuck with the way
yeah,
they did it.
that's probably it. Counts, charges, formal charges, tests. All right, so we're in our list of outcomes. We did hybridization practice. So Lewis structures. I have a really good Lewis structure GSA here. I have you going through that. And I don't think I give you the quiz in class, but I have you do it as part of the homework. So I'll let you do that. Let's check out the quiz really quick here. That's a pretty good one. So what I'll do is I'll just make up a Lewis structure question for us to do now on our Jamboard, which I have linked in today's lecture area. So Jamboard's here. Oh, so this screen capture these outcomes. We're kind of going over now. Chapter outcomes. All right, so a number of these I'm just going to let you do on your own as you go through the GSAs. You'll get it, and it should be review. But I want to do an example of a good Lewis structure that kind of incorporates most all of this. Let's go with so first off, the full way to do this is you can add up all your valence electrons, and I have you go through that with this GSA, but I'll just jump to the chase on this one. It would kind of be hard to do this one just as is with that formula. It would be easier if I wrote it out a little more detailed like this: CH3, C, put like a double bond NO, something like that to really emphasize what's going on. I think if I gave you this as like an exam question, it would be not enough info. I'd give you more connectivity like that. So let's go with that. So I have my carbon, and this carbon has 3 hydrogens on it. And I'm going to give the atoms lone octets and see what I come up with when I do that. You know what? I think I want another H in this. Yeah. Sorry. I made a mistake here. I guess I'd do it there. H4. There we go. Okay. So the first thing I do is I draw it out and I try to give everybody octets like that. And then I'll check for octets and formal charges. So does this carbon have an octet? What do you think? Does that carbon have an octet?
Yes.
Yes, it does. And I know it has an octet because I just count 1. Oh, I'll do it with my laser pointer. Yeah. 1, 2, 3, 4 bonds to the carbon. So that's 2, 4, 6, 8. We got an octet. What about this one over here? Does this carbon have an octet? Two, 4, 6, 8. Yes, looking good. And then the nitrogen, does it have an octet? Two, 4, 6, and the lone pair counts as 2. So that's 8 as well. Yep. They all have octets. And, or not, I didn't check oxygen yet. So far everybody has an octet. What about this oxygen here? 1, 2, 4, 6, 8. Yes, got an octet. We're looking good on all these octets. I'll go to the next panel. Yeah.
I have a question.
Yeah.
If you single bound that nitrogen, is it going to be the resonance of the molecule, or you cannot do that?
I didn't understand what you said at first, but yes, this will have resonance.
I mean, if you want to draw the resonance of the molecule, it's going to be the single bond between the nitrogen and carbon.
Yeah, we're about to do that. You'll see that in just a second.
Okay.
Good question.
Okay.
Continue. Okay, so I'll go to my next panel here. I redrew the molecule. And now I have to determine if there's some formal charge to this molecule. Because I know the formula has got an overall negative charge. Let me go back to that. It's C2H4NO. Oh, I took off the minus, didn't I? NO minus, okay. So we started with C2H4NO minus. So I have to have a formal charge somewhere because the formal charges all have to add up to that -1 overall charge. So does the carbon have a formal charge? Let's do a quick check on it. So for this carbon, it's formal charge equals group. What group is carbon in? 4 minus 4 bonds. Minus 0 electrons, so it has 0 formal charge. That's good. Same goes for this carbon. How about this nitrogen? Formal charge equals, what group is nitrogen in?
Five.
Group 5, good. Minus how many bonds?
3.
Thank you. 3 bonds. Minus how many electrons?
2.
2 electrons. So 0 formal charge, looking good. And now this oxygen here, group what?
6.
Group 6 minus how many bonds?
1 and
Minus 6
6.
electrons. Oh, we got a -1. So that's where our formal charge is. So we got to add -1 formal charge to that. And then I had a question about oxygen's formal charge. It does have a -1 charge. I had a question about its octet. It has a -1 formal charge and an octet. So 2, 4, 6, 8. So it's an octet. Okay, so if we have that -1 charge on the oxygen, and we're set up in a situation where we have like a lone pair, a single bond to an atom, and then a double bond to another one, we're set up for resonance here. So resonance has like one of the major resonance things we'll see a lot of is we'll have this kind of pattern, like an X double bond Y to Z. And I'll color code it too. This is like a resonance motif we see all the time, a resonance pattern. I'll use motif. Sounds like we're smarter if we use that one. I don't know how to spell it though. Motif.
No E.
So I sounded smart till I couldn't smell it. Motif. Resonance. Is there two P's in pattern? Pattern? I don't know.
Yeah, you're good on that.
Cool. So if you have a negative charge, if you have something like this, it's let me really point it out here. You have a lone pair, and then you have a single bond, double bond. Then you could you have resonance. So that's the pattern there. So get back and then edit this. Lone pair electrons, LP, to a single bond, to a double bond. We'll see that over and over and over. So it's good to recognize it. When you have that pattern, then you can have resonance. And here's how we draw it. I like to use curved arrows for resonance. I want you to as well. So this lone pair can come over and become a double bond right there. Then the pi bond can become a lone pair on the X. And these are the resonance. That's the resonance double-headed arrow there. So I have a pi bond in red, and on the X, I have a new lone pair. It'll have a negative charge as well. And there we have it. So do you see that same pattern here? I've got a lone pair, single bond, double bond. Let's emphasize that. Lone pair, single bond, double bond. There we go. All right, let's do it. Should we color code the lone pair and the pi bond for this one, or just keep it black for now? What do you think? Color code or keep it black? What's the vote? Color code it is. Okay. I'll make this lone pair red on the oxygen, and I'll make the pi bond on the nitrogen blue. There we go. Okay, so the way we draw the resonance is we have the lone pair come down and make the pi bond, and the blue pair of pi bonding electrons become a lone pair. And we draw our resonance double-headed arrow like that, and we have our resonance. There we go. So I've shown the arrows and the electrons move, but I haven't addressed the formal charge, have I? So I had initially a negative charge on this oxygen. So do I still have that negative charge on that oxygen?
No.
Resonance structure? No, huh? Let's check it out really quick. So the formal charge of this oxygen is group 6 minus how many bonds?
2 and then 4 hydrogen or electrons.
Minus 4 electrons. So that's, oh, I didn't put 6 by group. I put S. For some reason, my mind, sometimes I mix up the number 6 and the letter S. I don't know why. So, but overall, 0 formal charge. All right, so we got, so that's not where it is. But wait, what about the nitrogen? Let's check it. Oh, and then also, does the, before we check the nitrogen, does this oxygen
That
still
should
have
have
an
a different
octet?
geometry.
Hold on a second on that. So the oxygen here, does it have an octet still? 2, 4, 6, 8. Yeah, that was an octet.
Yeah.
Well, while we're in octet mode, what about the nitrogen? Does the nitrogen have an octet? 2, 4, 6, 8. Yep, looking good there.
Yeah.
Formal charge though of the nitrogen. Let's do it. So it's group what?
5.
5 minus how many bonds?
2.
2 bonds minus how many electrons?
4.
4 electrons. So that's 5 minus 6, that's minus 1. Okay, there's our formal charge. We got a negative charge on that nitrogen. Okay, so overall the molecule, in my resonance, I made sure my formal charge is right. Whatever formal charge I have for one resonance structure, it's got to be the same overall for the other one. So this resonance is just showing how this negative charge can be shared between the nitrogen and the oxygen. So when we have two resonance structures, it's a tool to help us see where things are. Like this tool helps us out. It says, oh, there's going to be a lot of negative charge on oxygen and nitrogen, and not so much maybe on the carbon. It's going to be mainly on those two, the resonance. And so we expect reactions of, let's say, something positive would be more at oxygen and nitrogen. Okay, so when we get yes.
That would also change the geometry of the nitrogen, right? That would be, instead of trigonal planar, it's now tetrahedral, right?
Yeah, that's a tough one, actually. So I think the nitrogen is still trigonal planar because the reality is it's a resonance hybrid. And so let me do a resonance hybrid and then ask me again. So now this one, let's draw now the resonance hybrid. So the resonance hybrid is a combination of these two resonance structures. That's more the truth, because these two things aren't like switching back and forth. They're not two different things switching back and forth. It seems like it. And that's why I'm very careful. You notice how I did not use equilibrium arrows between the resonance structures, because that would suggest it's like sometimes it's this and sometimes it's that, and it's going back and forth, but it's not. It's a combination of the two. And so resonance isn't really reality. It's just a tool to help us then draw more reality, which is the hybrid, the resonance hybrid. You could think of it as lots of analogies. There's lots of analogies like I'm Irish, Italian, and Dutch. So if I was like a resonance of my Irish, Italian, and Dutch, does that mean like one morning I wake up, I'm all Irish, like, top of the morning. And the next morning, I'm in equilibrium. Now I'm Italian. So I'm like, hey, let's go get a cup of coffee. Let's go take a break. And then I'm Dutch, and I don't know, got a good Dutch accent. Do we? I don't know. So I'm not switching back and forth between my Irish, Italian, Dutch. I'm a combination of them all. So these resonance structures aren't switching back and forth, they're a combination of them. So we have to draw. Oh, no worries. Okay, so we are back. And so when I'm looking at this guy, I want to draw a resonance hybrid. So I'll put a text.
I do have a question though regarding what I was saying about the geometry. Would that affect like where the hybrid would be leaning towards most?
Let's draw it real quick first, and then the hybrid, and then we'll look at the geometry. Good questions about the geometry. All right, resonance hybrid on next panel. Let's do it. I'm redrawing it on the next panel, which you can't see currently, but I'm just doing it so I make sure I don't make a mistake here. Nitrogen. Oh. I'm rusty on lecturing on Zoom. Gladly rusty. Okay, I'll bring you over now. So I've got my two resonance structures. I'll make that oxygen prettier. Okay, there we go. So we have to determine what the major resonance structure is. So because the major resonance structure, it helps us determine when we draw the hybrid, whether the hybrid looks more like one or the other. So whatever we determine is the major resonance structure, the hybrid will look more like that. So what do you think? Let me try to talk you into making the wrong decisions here. Let's see. So the left one has negative charge on the more, or yeah. More electronegative oxygen. So that's the left one. The right one has the negative charge on right. Negative charge on the less electronegative nitrogen. So what do you, in terms of that, which one do you think is the major resonance structure?
Left.
Yes. Because the oxygen can handle that negative charge better. That's how I think of it.
So if there was a positive charge, it should have been on the nitrogen.
That's right.
So if you were to put this in the NMR, would it look like the one on the right if you raised it from like alpha to beta? Is that where we're going with this?
Actually, let me draw the hybrid before we talk about that. So when we draw the hybrid, I want to draw it in the right geometry too. So let's go with, for example, this guy. What's the geometry of this carbon here? It's got 4 atoms attached to it.
Tetrahedral.
Tetrahedral, and it's
sp3,
sp3, right? Good. What's this carbon here?
trigonal planar.
Yeah.
Trigonal planar, sp2.
Two.
So now the geometry of this guy is kind of like, whoa, what's going on? That's the good question we got earlier from, I think, Michael. That's a good one. So let's draw the hybrid before we get to that. But we'll, since we know the other ones, we can already start on those. So here's the hybrid. So okay. So I draw my hydrogen to my carbon. Oh, and I want to draw out the longest line of atoms in the plane of the page. Like this. I'll draw it the other way. That's kind of could be confusing. So I've got my longest line of atoms in the plane of the page, and then I add in my other groups with wedges and dashes if needed off of that. So this first carbon right here, I'll number it so it's real obvious. Carbon 1, carbon 2. Carbon 1, what do I need to draw on it next? 2 more hydrogens, right? And what geometry? Trigonal planar. So should my hydrogens be pointing like wedge and dash up or down? They gotta go down. Otherwise it wouldn't be a tetrahedron. All right, we got those 2. And then carbon 2 has the bond to nitrogen and oxygen. And it's a hybrid, so I'm going to draw it like this. oxygen will have 2 lone pairs always, and then it's got the other lone pair in resonance. So I'll draw this dotted line to represent that up towards the oxygen like that. And the nitrogen always has this other lone pair too. Okay, so now this means the oxygen and the nitrogen are sharing this -1 charge. Should I put -1/2 on each of them? No, what I should do is put a little more on the nitrogen. I'll call it like -3/4. And then I'll say that nitrogen only has -1/4. So I pick that because I'm saying that the nitrogen will have more negative charge than, I mean, the oxygen will have more negative charge than nitrogen because it's the major resonance structure has the negative charge on oxygen. Does that make sense? Okay. And then next I'll do some dipoles. Oh, and so the geometry, I'm going to go with this still being trigonal planar for the nitrogen. That's kind of a hard one because of the resonance to it. But that's how I think of it because it's always got that pi bonding going towards it. So it's going to be trigonal planar. And in terms of NMR, I'm not sure what your question was about NMR, but I'd expect for NMR like 1 hydrogen singlet and then another 3 hydrogen singlet, a couple carbons in the carbon NMR. Okay, so now let's look at dipoles. Bond dipoles.
Do you know if the AC is only out in the museum there, or is it any other parts of the school?
Yeah, they listed off some buildings like the M building and the S and the ST buildings. It should be in the email you got.
Okay, thank you.
But not the whole campus. Okay, so I've got my resonance hybrid. I'll put the and I'm not exactly sure I don't think it's exactly -1/4. I just know that it's going to be less than can't write right now. It's going to be less than -1/2, which I just wrote. -1/4. We'll say, I'm just guessing it's -3/4, -1/4. I'll add up to 1, and it's one's more than the other. Okay, so now dipoles. We use dipoles like this, bond dipoles. We show them as an arrow with a plus symbol at the end. This is the positive end. And that's on the end of the less electronegative atom. And so this is here, that's the negative end. Trying to write fast and it's making me sloppy. I have to rewrite it. Negative end. And so that one is like the more electronegative atom. Okay, so for instance, when I look at carbon and hydrogen, who's more electronegative of those two? So remember, I want us to think of sp3 carbon as less electronegative than a hydrogen, actually. And then sp2 carbon as more electronegative than hydrogen and on. So I'm going to draw a dipole between the carbon and the hydrogen, but it's going to be tiny. See this little dot? See that dot right there? That's the dipole moment. Oh, and the length of the dipole is the magnitude. Let me put that up here really quick. So a dipole like this is weaker than one like this. Stronger magnitude of dipole for this one.
Is the biggest dipole that we can have that of hydrogen and fluorine?
No. Other atoms are less electronegative than hydrogen. I guess it would be if you had any kind of covalent bonding between fluorine and the least electronegative atom, that you still consider it to be covalent, more covalent than ionic. All right, so this dipole moment I drew right here. I'll zoom in on it. Here's our dipole moment. It's tiny. It is, I like to think of it pointing towards the hydrogen, but it's really small. It's so small that we can ignore it. Okay, so I've got that little tiny dipole moment, and then I've got another one here on the wedged out and another one on the dash. So I've got these dipoles, right, that are so small we don't worry about it. What about between the carbon, these two carbons? Should there be a dipole moment between those? Yeah, they'll be tiny too. There'll be a dipole moment just barely pushing towards the other carbon. Why is that? Why did I draw a dipole moment between two carbons of the same atom?
Is it because one has the nitrogen attached to it, the nitrogen and oxygen?
That actually plays a part in it, but I was thinking more along the lines of that's an sp3 carbon and this is an sp2 carbon. So sp2 carbon is more electronegative, right, than sp3?
Yeah.
Okay, and now for the more serious dipoles, carbon to nitrogen. Is there a bond dipole there? Who's more electronegative, nitrogen or carbon? Nitrogen. So I draw the bond dipole towards nitrogen, because nitrogen has the negative charge. And then carbon to oxygen, that's the other one. Yep, I'll draw it a little bit longer because oxygen's even more electronegative than nitrogen. There we go. We got our bond dipoles all drawn in. And then we end off this with drawing our molecular dipole. So for the molecular dipole, I'll redraw the molecule. And I just kind of visually add up the dipoles. Don't have to do any serious math here. Just looking at these dipoles, I consider these ones are so weak, they don't really matter. This one is pretty weak, it doesn't really matter, but these two are the strong ones and they're both pointing in that direction. So my molecular dipole, I would say, is like this. Oh, you know what? There's one more too. I forgot one. I forgot the NH bond dipole. So that one's going to go like this, like that. But I think that's not going to really override these other two. So there we go. We got our molecular dipoles, just kind of a sum of the other ones. Yeah, that's fine. Okay, so we got that. And so overall, I would say this molecule is a polar molecule because it has a bond dipole, a molecular dipole, and it's got charge. All right. Now, I want to give you one. I wanted to start sigma and pi bonding diagrams, but the lecture on Zoom is going slow. But I still will do a little bit of it. But before I do it, I do want to give you one of these tricky ones. I like these ones. Let's go with. Okay, yeah, that's a good one. So. I have this molecule here. It's protonated acetone. So protonated acetone. Does this molecule have resonance? Let's see. We have oh wait. This isn't the one I wanted to do. Yeah, this is the one I wanted to do. This one doesn't follow the trend of the lone pair single bond double bond, or split. That's okay. So
It
but
looks
this
like
does
it
have
could have a resonance.
Yeah, it could have resonance. I'll make this bond red. This can resonate up into the oxygen like that. And when I do that, the carbon winds up having, whoa, that was weird. The carbon winds up having the positive formal charge now. So I have resonance between these two atoms. I have on one of them, I have the positive charge on more electronegative oxygen. And then on the other one, positive charge on less electronegative carbon. So, which do you think is the major resonance structure?
Positive charge on carbon.
So this one's a tricky one.
Left one.
You'd think it's going to be, oh, the oxygen doesn't want a negative charge, positive charge. It's more electronegative. But we also have to consider something else.
This is the bond stability.
Octets. So consider octets before octets override electronegativity differences, trends, considerations. So with that being said, we got to go back. We can't just look at electronegativity on this one. We got to also look at octets. So does this carbon here have an octet? 2, 4, 6, 8.
Yes, it does.
Octet, good. What about the oxygen?
Yes.
2, 4, 6, 8. Yes. Good. So this resonance structure is the all octets resonance structure. All the other atoms that want octets in that molecule also have it. This carbon has 3 hydrogens, so it has an octet. So is that one. The hydrogen doesn't want an octet. It has a duet that makes it happen. Okay, but what about over here? Does this oxygen have an octet?
Yes.
2, 4, 6, 8 looks good. What about the carbon though?
No.
No. So that changes things. So that one's got only 2, 4, 6 on it. 2, 4, 6. No octet there. So it winds up the left one's the major resonance structure. So this one's the minor resonance structure over here.
Does that affect it more or less than the other rule?
So if you have to consider octets first, then you'd consider where the formal charge, where things are. So whenever you're doing these considerations of major minor resonance, first consider octets, then look at formal charges. On the last example, I kind of set you up to get the next one wrong. On the last example, if you look when we were choosing majors, this nitrogen has 2, 4, 6, 8 has an octet. Over on the resonance on the right, 2, 4, 6, 8. It's all octets. The oxygen, 2, 4, 6, 8, all octet, 2, 4, 6, 8. Yeah. So on this one, everybody had an octet who wanted an octet. So then we went to the formal charge considerations. On the other one, we had to look at, we did it more completely, and we looked at the octets first. All right, let's see what we got. We got 3 minutes. Okay. I'm gonna do a really fast sigma and pi bonding diagram. So at least I got one going. Did many of you do these in general chem, or any of you? I'll do this molecule first. Remember this one, 1, 2, 3, 4, 5. I'm gonna do this one kind of fast, and then I'll go through more examples next lecture. So for sigma and pi bonding diagrams, I like you to draw out first just the sigma bonding diagram all by itself, and I'll show you how you do that. The first carbon there is carbon 5. So I'll draw that out and a little 5 by it. And then I'm going to draw on, gotta give myself lots of room for these. I'll draw in my hybrid orbitals. So that carbon 5 is sp3 hybridized. So it's going to have an sp3 orbital coming up to bond to carbon 4 like that. And then another one in the plane here. So these are my sp3 orbitals. This one to the left has a hydrogen bonding to it. That's the hydrogen s orbital. It's not hybridized. And then I like to draw these kind of 3D. This is my way to draw the other sp3s hybrid. Other sp3s in 3D. I put a wedge in one and a dash in another. And then I add on my hydrogen. I kind of draw this one overlapping and this one's looking like it's behind. Give that 3D effect. So this is an S again, an S, and then this is, my 5's kind of ugly there. sp3 here and sp3 there, good. Okay, so I've really gone into detail to show you how that bonding works to carbon 5, and now I add in carbon 4, and it will be sp hybridized. Look like so. And it has a hydrogen off of here. Carbon 4, sp2. I think, did I say sp hybridized? sp2. Okay, moving on. Carbon 3, it's also sp2 hybridized. I don't like the way I do that one. SP, yep, trigonal planar here. There we go. And we've got a hydrogen down here. sp2, 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 got it. And that is carbon 3. And now we're going over to carbon 2, the alkyne carbon. It is sp hybridized, so it's linear. And it will sigma bond to carbon 1, sp hybridized as well. SPS, okay. And I think that's it. Yeah, just forgot to label number 1 there. Kind of got small on my carbons for some reason. Sorry, I was zooming in and out. So that's how I do the sigma bond diagram. I just draw out all the orbitals, that sigma bonds. And I'm also kind of abbreviating things. So like when I draw my hybrid orbitals, they really have like a little nubbin thing like this. Say this is my sp3. I'm gonna just say it's draw just the big part of it. Otherwise it gets to be too much. So this is like, say, like an sp3. It's still an sp3. I left off that little nubbin in the back. And finally, for the pi bonding diagram, when I draw those, I draw all the sigma bonds as just bond lines, wedges, and dashes. So I'm just going to abbreviate all my sigmas like this. And then I will, wait, I didn't do that right. Did I do this right? Okay, so let me number them all. 1, 2, 3, 4, 5. Okay, so I draw on all my sigma bonds like that. Then I add my leftover p orbitals. So on carbon 4, I've got this leftover p orbital coming in and out of the plane of the page. We reviewed that at the very beginning of lecture, right? Carbon 3 has the same type of p orbital. and coming in and out of the plane of the page. So these are lined up to make my pi bond. So that's my pi bond that I'm describing right here between 3 and 4. I'm showing it. Pi bonding is electron overlap above and below the internuclear axis. Okay, and then over here at carbons 1 and 2, I also have leftover p orbitals. So I got one in the plane of the page that lines up perfectly with this one. So they're going to be bonding like that. And then I also have p orbitals coming in and out of the plane of the page. And they're bonding to make the second pi bond. So there's one blue pi bond here, bonding above and below the internuclear plane, and a p orbital, a green one, also doing a pi bond above and below the internuclear plane. So that's why you have a triple bond there. So we'll be doing these. We'll practice more next time. The sigma bonding diagram separate from the pi, and then the pi, you draw the sigma as like lines, wedges, and dashes. All right. Thank you so much for coming. And we all got through it. Another online lecture. I am recording this video and I will post it later too, for those who couldn't make it. And I'll have office hour. Let's take like a 10-minute break, and then I'll make another Zoom for office hour. So come on over to the office hour, and I'll link the office hour in the normal spot, and